Welcome to the Fractional Calculus seminars. Today we have Professor Bruce West, who was a chief scientist in mathematical and information sciences at the US Army Research Office from 1999 to 2021, retired in July 21. PhD in physics from University of Rochester in 1970. Over a 50-year career, he has published 24 books, including those mostly closely related to this colloquium, a crucial event rehabilitation theory, Springer Briefs in Bioengineering 2023, Crucial Events World Scientific 2021, Fractional Calculus View of Complexity, Tomorrow's Science, CRC Press 2016, Nature's Pattern and Fractional Calculus de Gruyter 2017. He has published over 400 scientific articles, essays, and opinions in referred scientific journals, garnering over 24,000 citations with an H factor of 80. Before ARO, Dr. West was a professor of physics at the University of North Texas from 1989 to 1999 and the chair of the Department of Physics from 1989 to 1993. He is a fellow of the American Physical Society and elected in 1992, and of the American Association for the Advancement of Science, elected in 2012. He has multiple awards for his research, including two prestigious awards given to civilian researchers, those being the Presidential Meritorious Rank Award 2012 by President Obama and the Presidential Distinguished Rank Award in 2017 by President Trump. We are very happy to have you here. Professor West, you may please begin your talk.
Thank you very much for that kind introduction, even though I wrote it. The topic of my talk today is complexity synchronization and the fractal calculus. I call it the fractal calculus rather than the fractional calculus because I think it was a misnomer that, for historical reasons, got perpetrated, and it's more accurately the fractal calculus. And as you can see from this pyramid scheme here, that these are 8 of my 24 books, all dedicated to either complexity synchronization or the fractal calculus. This is a lion's share of my books. I show them to emphasize this quote by Charles Darwin in 1887 in The Voyage of the Beagle. He wrote this in the preface. I have long discovered that geologists never read each other's works, and that the only object in writing a book is proof of earnestness, and that you do not form your opinions without undergoing labor of some kind. And this just is proof of earnestness, and it's a labor of love. But as you will see, this is still science, and it's actually it shoots away from physical sciences. I'm a physicist, into the domain of complexity science, and it's how can you use knowledge of that kind, and how do we characterize complexity? And I've annotated the references at the end of the talk, and these are all, the first ones are about inverse power laws. And how do complex networks share information? This is the heart of the talk, that there's a new kind of resonance that's called spectral resonance or complexity synchronization, in which you do not, in normal resonance, you share a frequency, and the phase determines how close you are in the resonance phenomenon. That is not the kind of resonance I'm going to talk about today. And another kind of question that arises are the principles that are discussed universal. And for the complexity matching piece of this, the answer is no, but for the complexity synchronization piece of this, the answer is yes. That the principles I'll discuss are universal. And so we'll talk about the significance of the research. A universal principle of complex networks has been formulated. And it's the information transfer can dominate the energy transfer. And information transfer is a maximum complexity time series match. And that's called the principle of complexity management, or complexity matching. A new theory of 1 over F noise, which is the signal, has been constructed for physical, social, and life sciences. So 1 over F variability is related to the complexity of crucial events. And what I'm doing here in trying to give you a background that's qualitative before I get into the mathematics. So the frequently asked questions about universal principles are the interactions of complex networks like thermodynamics, and can't we just use the methods of non-equilibrium statistical physics to address network science? And the frequently given answers are yes, no, and sometimes. And we'll see the reason for that in this talk. So this overview is intended to prepare you for the remarkable results obtained by theory and verified by observation, and that are presented in this seminar. An organ network is it communicates via the crucial event time series x of t. An organ network is like the lungs, the heart, the brain. They are organs, and as you see to the right there, the time series for the brain looks like a random process. It's not, but it looks fairly complicated. The time series for the lungs look like a nonlinear water wave. They're just big bumps. And the time series for the heart looks like at most a bimodal distribution. A big blip followed by a little blip. And you'd be hard-pressed finding any two time series that are as dissimilar as these three are from one another. And yet, I maintain from the research that we've done in our group that these time series are in resonance with one another. But we have to be careful about how we define resonance. These crucial events have temporal scaling. Crucial event time series have temporal scaling, so that if you take x of t to be the time series, and you scale the time intervals by lambda, you can factor out a lambda to the delta times the original time series. And delta is what we call a scaling factor. And this is going to be all important in this talk. The scaling index, or scaling factor, delta t, provides a measure of the temporal complexity. So this we're going to use as our working definition of complexity in this talk, this factor delta. And why do traditional statistical measures used in medicine fail is another thing we're going to talk about. And it fails because when you talk to a physician about probability theory, he'll talk about the normal distribution, or the Gaussian distribution, as physicists call it. And that's a one-humped distribution. It has a mean, and it has a variance, and the mean characterizes is typical of the process being measured, and the width of the distribution tells how well the mean characterizes that process. Now, inverse power laws replace normal statistics of 1 over F variability. And this is an all-important result, and we'll see what it means subsequently. complexity synchronization enables the brain, heart, and lung triad, the brain time series, the EEG, to exchange information with those of the heart and the lungs, and all the other organ networks in the body. Complexity synchronization is a consequence of the existence of complex or crucial event time series. Now, what I hope to prove, what I'll show you is that the three different kinds of time series that you have for the brain, heart, and lung, shown in the top cartoon there on the upper right, is by means of this processing technique, which we call the diffusion entropy analysis, gives rise to when you determine what the probability density is from data, you can construct from the p log p minus p log p form of the entropy that the shift in entropy for time t from a constant reference value is equal to the delta of t times the log of t. And so when you take the say these 20-second or so time series that look nothing like one another, the brain, heart, and lung on that upper slide, when you transform it, when you construct the entropy and take the entropy as a function of log t, you get these three top curve here there. This top curve between these 2 points is the 20 seconds of interest, and you see that the three time series, the EEGs, the respiratory system, and the ECG, form these straight lines. So we go from three time series, which are nothing like one another, apparently, and by looking at their entropy as a function of time for short time intervals, you get these almost parallel lines, but they're not quite parallel. This is what we call the complexity synchronization. And the empirical data suggests a new way to conduct rehabilitation using this diffusion entropy analysis to determine the quasi-periodic scaling of the triads. And I'll show you what I mean by that. So how does a fractal calculus come into this picture? Well, the scaling probability density function with a scaling index delta t is the solution to a fractional Fokker-Planck Kolmogorov equation. Now, this is a generalization of the Fokker-Planck Kolmogorov equation to a fractal, and that fractal is determined by delta t, which gives the fractal dimension of the process under investigation. So let me go back now and start slowly, and you'll see where all of these things come from. This was my road to understanding complexity. Gauss, circa 1800, when he was 19 years old, he wrote a paper on the twinkling of stars. That the position of star was undetermined because as the starlight entered the atmosphere, the turbulence in the atmosphere shifted the phases in the constant shining light, and so it seemed to dance around a point and have a mean value and a variance. And when his determination of the spell-shaped curve led to a simple scientific worldview. The world is linear, the output is proportional to the input, and, well, let me do them in parallel, because a century later, Pareto came to a much different conclusion about the nature of the world. And whereas Gauss could talk about a simple wooden bridge that could last for a century or so, Pareto's inverse power law distribution led to the description of the Tacoma Narrows Bridge disaster in 1940. This bridge that was concrete and steel and steel cables came rushing down because of the singing of the wind through the cables, setting up a resonance frequency through the bridge that brought the cause of the disaster. So the simple scientific worldview of Gauss is replaced by the complex scientific worldview of Pareto. And whereas Gauss had a linear view of the world where the output is proportional to the input, Pareto had a nonlinear worldview where small changes may relate to divergences. For Gauss, the world was additive. For Pareto, it's multiplicative. The simple rules yield simple results in Gauss's world, but simple rules yield very complex results in Pareto's world. The equations of motion were stable in Gauss's world, but unstable in Pareto's world. And it's predictable in the simple worldview, and the predictability had a limited horizon in the complex worldview. Everything in Gauss's world is quantitative, but in Pareto's world, the qualitative could be equally important to the quantitative. And the end result of his discussion was a normal distribution. And the end discussion of Pareto is that the inverse power law distributions are what you actually see. So this is a slide I put down to show you three quantities and their interrelationship. In the bottom here, we have the scaled variable x of t goes like t to the delta, or it could be t to the delta t. And this is the scaling behavior of the time series, which are a sequence of discrete crucial events. At the top here, we have the waiting time distribution that we look at. The way in which this view of the world came about was through Feller's introduction in 1948 of the renewal process. And he talked about renewal processes as like a Poisson process in which you have a sequence of discrete events, and the time intervals between the discrete events are statistically independent from one interval to the next. He also further introduced the notion that the crucial event was a renewal event in which the time series is an inverse power law. So you have a renewal event when the time series is inverse power law becomes a crucial event. And the waiting time is this inverse power law t to the minus mu, where mu has a range of indices between 1 and 3. Now, you can also show that the power spectral density for this function, when you take the Taylor when you go to a spectral representation of the time series, you expressed in terms of the frequency, you get a beta, or a minus beta for the exponent. And that beta can be related to the mu that's in the waiting time this probability density function. So beta is equal to 3 minus mu. You can also relate that to if the function is truly renewal, then it has a delta, and the delta can be related to the waiting time distribution index, mu. And so when mu is between 1 and 2, the system is non-ergodic, and delta is equal to mu minus 1. When mu is between 2 and 3, the system is ergodic, and this is form the basis of the Maxwell-Boltzmann distribution and all the physics work that was done in the 19th century by Maxwell and Boltzmann. And delta is equal to 1 over mu minus 1, and mu is between 2 and 3. And when delta is equal to a half, mu is greater than 3, and the distribution is Gaussian. So we have these three indices, mu, beta, and delta, and I'll talk about each of them in turn. Well, they'll come up in the discussion of the complicated nature of the time series you want to look at. But we have to draw a clear distinction between what happens when you have a normal statistics and what is special about inverse power law probability density functions. Now, complexity means, as discussed by Pareto, results in inverse power law, and then that subsequently became associated with the fractal dimension some 50 years later. So say you're up for tenure, right? And there's always one person on the committee that looks at your publications in detail and says that, well, your publications, if you look at the average number of publications, the number of citations to publications in a year, this is a plot of all the publications in a year, and it was done by De Sola Price in the 60s. And what you observe is that for the first 35% of all the publications in science, that there are no citations. The next 49% had one citation, and so on down until you get to the average number of citations, which is 3.2 per year. Now, what's remarkable about this, and it's how you respond to the curmudgeon on the tenure committee, is that this is the average number of citations is out in the 4th percentile. You've exhausted 96% of all the scientists in the world that publish less than average. So that you look at this and you say being average is truly exceptional in the Gauss's worldview, whereas in the I got that backwards. In the Gauss's worldview, being average is typical. That's characteristic of the distribution of the quantities you're looking at. When you have an inverse power law, however, that's not the case. In the Pareto worldview, when you have an average value, you're already out in the 96th percentile. And so being average is truly exceptional. And the average never characterizes a complex phenomenon. And that's talked about in this 2006 book, Where Medicine Went Wrong. The entire book is a discussion of where the medicine went wrong is that it adopted the normal distribution to describe physiology and physiological time series uh, rather than the inverse power law. And the inverse power law is what dominates, and that's where medicine went wrong. And so for power laws, our phenomena are strange when we come at it from the Gauss picture, because most workers earn less money than average, most researchers publish less than average, most scientists are cited less than average, speakers use fewer words than average, and because all of these things that you use to characterize the system do not have normal statistics. They have these inverse power law statistics. Now that's a key feature of the world, and in particular, we're going to talk about what happens in your physical body. We're going to talk about fractals, and a fractal is something that's you have a large, like this tree on the left there, and you look at the small nub out in that square, and you magnify that, and what you see in that nub is a duplication of the large scale structure. And if you take a nub at the end of that and magnify that, you again get the original view. And so this is a geometrical fractal. It's tree-like. It's self-similar branches. Structures repeat itself on all levels of the hierarchy. Magnified branches at each level. Branches within branches within branches. But that's not the most use. That's a useful form of fractal. But what you see in physiology very often is this time series, and this is the heart rate time series, and the time interval for the beat changes in this intermittently erratic matter. So that if you have 300 minutes of data, and you look at the first 30 minutes and put that on the same display, you see that the 30 minutes replicates the 300 minutes, and if you take the first 3 minutes of the 30 minutes, that looks very much like the statistical nature of the 30 minutes and the 300 minutes. So that's a statistical fractal, and the time series, that's for heart rate regulation. And fluctuations are self-similar in a statistical way. You have clumps within clumps within clumps. And when you look at the trees on the left, the boxed-in time series is the scaling of the tree, and the boxed-in time series on the right is the scaling of the probability, going from one scale to the other. And then this becomes the linchpin for the further discussion, this notion of the scaling of the probability density. Now, exactly what are crucial events? Time series. Renewal theory plus inverse power law waiting time distribution entails complex crucial events with scaling index delta. A crucial event time series has a fractal dimension. D is equal to 2 minus delta. So that if you know the scaling index, or you can determine the scaling index from the data, you know the fractal dimension of the time series. You know further that the fractal dimension D is a measure of the complexity of an organ network time series, and that the complexity is the level of information generated by that organ network. And then the fourth is putting this all in the back to the table where you have the waiting time distribution, and you have the interval mu between 1 and 3, and d is the fractal dimension, and so on. So why use information variability rather than energy variability to describe the behavior of a crucial event time series? Shouldn't the energy variability be sufficient? Well, not according to Norbert Wiener. In 1948, I guess 48 was a pretty big year. He wrote a popular article. By popular, I mean there was very few equations in it. And he actually constructed the first universal principle of network science. And he started with the second law of thermodynamics, that the high energy network and a low energy network, that energy flows from the high energy network to the low energy network, and that's the direction of the influence. What's usually not mentioned in that discussion of the second law is that the entropy is approximately equal in those two cases, when to have the energy go from the hot to the cold. When the energies are approximately equal, or one's a little bit greater than the other, but the information or entropy in the systems are vastly different. For example, if you have a low information network in the high energy system and a high information network in the low energy system, then it's the information that flows from the high information system to low information system, and that you see that the cold system is influencing the hot system rather than the other way around. And that looks like a violation of the second law, but it's not. When one looks at this phenomenon like osmosis, that's actually controlled by the entropy of the information, then rather than the energy, you can have a cold fluid going into a warm fluid because of the osmotic pressure. So given the proper conditions, the force between complex networks produces the energy gradient in one direction between the networks, and that can be overcome by the force produced by the entropy or information gradient acting in the opposite direction between the networks. And this is here we use the complexity as a measure of the information, and so that becomes our working definition of the information flow as the flow of the complexity. So an integer order calculus probability theory, number one. This is where most physicists are introduced to the probability calculus, and it's using the BSCK chain condition. B is, these are the authors, Bachelier, Shmakovsky, Chapman, and Kolmogorov. They don't, most physicists don't realize that the Bachelier, the first author in this chain condition that relates the probability density that goes from an initial state to an intermediate state, from T naught to T prime and X naught to Z, and then from T prime and Z to T and X. And you sum over all the possible intermediate states, and you get the closure of the P of X to T at X naught and T naught. Bachelier did this for his PhD thesis, and he actually proved everything that Einstein proved 5 years later. He was a student of Poincaré in 1900, and he derived all the conditions for Brownian motion that Einstein did 5 years later. And that took off with Einstein's second publication, in which he said he heard of this blue moon biologist that had done these experiments with the heavy particle and light particle fluid, and reproduced his result. He said he thought that these were the experiment. Could be the experimental justification for his theory, and that became Brownian motion. So we follow Kolmogorov's argument and construct the Fokker-Planck Kolmogorov equation for the PDF from the chain condition. So assumption one is that the PDFs are stationary, which means that the PDFs, that it's an ergodic system, and mu is between 2 and 3. And most of what's done in physics, like the Maxwell-Boltzmann, as I mentioned earlier, make this ergodic assumption. So in this new notation with z equal x naught equals 0, and alpha equals 1, we set the delta t is equal to, the notation is that the change in the probability density when alpha is equal to 1 is equal to delta t times the derivative of the probability density plus a correction of order delta t squared. And I'll talk about the alpha not equal to 1, less than 1, subsequently, after I finish this review of the traditional derivation of the Fokker-Planck equation from the chain condition. So when alpha equals 1, we substitute in the chain condition 1 and using assumption 2, which is that as delta t goes to 0, that this stationary ergodic probability density is a delta function in space. And that leads to a time derivative on the left, and the limit is t delta t goes to 0, 1 over delta t is the integral minus the delta function in x and z times the probability density. And to make that clearer, you take the expansion of the PDF, which in first order it's a delta function, and the second order delta function is a, which is a first moment times the derivative of the delta function plus the second moment, and it's the second derivative of the delta function. And these were the assumptions made by Kolmogorov. And you put this into the integral equation, and this reduces the integral equation to a fractional term. Well, you just get that this is the Fokker-Planck Kolmogorov equation, in which A1 is and A2 are the empirical representations of a process being modeled. A1 is the first moment of the process, and A2 is the second moment of the process. And the higher order terms contribute negligibly. And you know that when A1 is equal to 0 and A2 is equal to D, that this is just the solution to the diffusion equation for a particle moving in space and time is a Gaussian distribution. Now, and this is where it gets interesting. This is the fractal order calculus probability theory. is also known as kinetic theory or fractal kinetic theory. But any kinetic equation is an approximate description of the behavior of an ensemble of particles or trajectories. In the sense that some details of the dynamics are neglected. So this means that the information regarding the network that we consider important, we intend to preserve. The type and structure of the kinetic equations, therefore, is dependent on our choice of variables that make up our reduced space and the level of coarse graining our trajectories. I've got some notes here that I went through. So the origin of the fractal kinetic equation is based on the existence of sticky zones in phase space, which are the remnants of the collapse of the hyperbolic fixed points due to chaos. Now you know that when you have a nonlinear system, the generic behavior of the system is to become chaotic, and the analysis has been worked out in excruciating detail, such that the hyperbolic fixed point becomes unstable, and the Poincare mapping and the region of that fixed point becomes blurred out, and this is when you calculate the average time for a particle or a mapping of a particle to leave that region of the phase space. It's an inverse power law distribution, and that inverse power law is what Zasletsky refers to as stickiness. So we can make the map of the trajectories dynamic as consisting of the capture within the sticky domains and neglecting their transitions between one sticky domain to the next. This followed by defining new support of the reduced part of the phase space. I'm sorry if that he's blowing leaves in the backyard, and this is what happens when you work at home. So if that, I hope that doesn't bother anyone.
Now it's fine. I mean, there is very little you could do about it. So, I mean, let's just go ahead.
You can still hear me though, can't you?
Yes, we can hear you. We can hear you. Yeah, that's fine. Is it possible to close the window?
Okay, we're at the point where we're talking about the fractal kinetic equations and how you get the different variables, or how you get the different regions of support in the phase space for the variables. And it's when these, if you ever looked at the maps, that you have these interconnected points, and then you have the webbing that is traces where the trajectories go, and when you reach a certain energy, that that begins to break up, and the hyperbolic fixed points become chaotic centers, and the new probability density is a construction of the stickiness of the centers, which are given by inverse power laws, so that you now have you can visualize a random walk from one center to the next, and you're at that center for an inverse for a time that's given by an inverse power law. And the new support is based on the observation that the set of sticky domains has a fractal or multifractal structure as manifest in fractal time. And this is where fractals become important in this discussion. And one of the things about fractals, if you have a function that's determined by, that has fractal properties so that it becomes a fractal function, it has no derivative, which means it has no equation of motion in the integer order calculus. And this is the reason that you have to go to the fractal calculus to determine the evolution of the system on this on these the distributed sticky domains that have a fractal distribution in phase space. Now, this means that the information regarding the network that we consider important, we intend to preserve in the type and structure of the kinetic equations, therefore is dependent on our choice of variables and make up our reduced space at the level of coarse grading of our trajectories. Now, we assume that the PDF is no longer the same in the fractal kinetic theory and follow the Zaslevsky implementation of Kolmogorov's argument to construct the fractal Fokker-Planck-Kolmogorov equation. And so now we look at the difference between 2 points of the probability density defined a la Zaslevsky using Hamiltonian dynamics, and alpha is a parameter between 1 and greater than 0 but less than 1. And so this can be generalized as the infinitesimal shift of P of x along T by delta T to the alpha. And one thing that's often overlooked is what specifically this means, is that when you're looking at, as delta T is going to 0, as it does in the limit, you're looking closer and closer at at a point on long T, and since alpha is less than 1, this becomes a magnifying glass, so that you see more and more of the region in the vicinity of T as alpha becomes approaches 0. And we define the case of the fractal time with exponent alpha between 0 and 1, which enables us to replace the expression resulting in the fractal Fokker-Planck equation as shown here, so that we have an equation that's a derivative in time on the left, a fractal derivative in time alpha, and we're taking the 1 over T to the delta to the alpha limit of the integral term, and the non-local piece under the integral. Remember, that's where we approximated the transition probability by the first order term is a delta function in the x and z. The second term is now, rather than being a first derivative and being the first moment times the first derivative of the delta function, is the alpha moment and the alpha derivative of the delta function. And the second term is the beta derivative and the beta derivative of the delta function. and these are well ordered. And this is where things become. And his masterful work, Zaslewski, proves that the A sub j for the first two lowest moments are z minus x to the alpha j, where alpha 1 is beta minus 1 and alpha 2 is beta, and divided by delta t to the delta, and the limit delta t goes to 0. And this yields the fractal Fokker-Planck Kolmogorov equation, or the fractal kinetic equation. And you can prove that with this definition of the average moments, that you can derive the symmetric derivatives d to the subscript the magnitude of x, and for beta between 0 and 2, you get the first term, which is between a symmetric spatial derivative between 0 and 1, and the second term is a spatial derivative between 1 and 2. And the A1 and A2 Zaslewski spends a great deal of time. Yes? Question?
No, sorry.
Okay. In his book, what's the title of his book? I can't quite make out the title. It's on the floor. But in his book that he wrote in 2002, he used a lot of the work of Mike Schlesinger's to arrive at this fractal kinetic theory equation, which is the simplest of the analogous diffusion equations, which A1 is equal to 0 and A2 is equal to a constant K. And so this just becomes the simplest anomalous diffusion equation that we can solve analytically. And Zaslewski uses the renormalization group approach to the equation. It shows that if you apply the renormalization group n times, then when you apply it to a delta x, you get lambda x delta x to the n. And if you apply it to delta t, you get delta t. You apply it n times, you get delta t to the n. And then the equation can be solved with delta x to the alpha, delta x to the beta is equal to lambda to x to the scaling parameter in space to the beta power is equal to the scaling parameter in time to the alpha power. And the solution is given when you have a sigma that's equal to alpha over beta. And so one can show that the solution to 11 is given by 12. And the P of x of t in the center is given by the inverse Laplace transform of the Mittag-Leffler function that's e to the alpha, where k to the beta is the Sorry, that should be the Fourier transform. Yes, not the Laplace transform. We've already done the Laplace transform. And you can show that this is related to the Levy distribution and so on. But what's important here, and this is the most important piece, is that the general form of the solution is t to the minus delta is times an unknown function x to the t over delta, x over t to the delta. And this is where the fractal calculus is all important. That this general form of the solution, you could drive it this way, which seems like there's a number of arbitrary assumptions, which I assure you the assumptions are not arbitrary, and you get exactly the same result if you use a much simpler method by Montrol and Weiss, called the continuous time random walk, and you have the same form of the chain condition, except for the continuous time random walk, you assume that both the step functions and both the steps and the times between steps are inverse power law. And when you make that assumption, you get exactly the same result that you get in 12, except you know what F is. So how do you relate this to time series? So how do you prove that these things are valuable, or they actually exist in the real world, the physiological world? So we use an empirical discrete time series zeta to consider the diffusion process x of t, and we just sum up the well, I guess there should have been a delta t here, because this should be like dx dt is equal to zeta. And so that the x of t is the integral of zeta of t minus t prime dt prime. And the question is, if the empirical time series zeta of t gives rise to an x of lambda of t that goes like lambda to the delta of x of t, it is an anomalous time series having scaling statistics given by the scaling PDF. And everyone knows that you construct a diffusion process because that allows you to get a probability density, an empirical probability density. And that empirical probability density is given by the Shannon-Wiener entropy. Well, it is used in the Shannon-Wiener entropy to get the entropy for the system. And this is the average information, log 2 of P of x of L, with the negative sign, is the information contained in the time series. And the integral over Px of L dx of that log 2 P is gives you the analytic form that the change in the entropy is equal to delta log t, which you recall I mentioned in the first couple of slides. So this is the crux of the talk. It's the heart of the talk, if not the brain. Simultaneous measurements time series for the brain, heart, and lung during neurofeedback training manifests a new kind of synchrony. So the question is, how can these three totally different looking time series manifest any kind of synchronization? The key to their unexpected behavior lies in the scaling of their scaling indices, delta as measures of complexity. when you use delta as a measure of complexity, you can show that it's the complexity that's being synchronized among these three vastly different looking time series. All three are crucial event time series and communicate by means of complexity synchronization. And this is the how you get to it. This is the process of the diffusion entropy analysis. And the empirical time series we use here is the heart, but you can use the brain or the respiratory time series, getting the same results. And what we get here is if you take this long time series and take about 10 seconds of it, or only 2 bumps, so you're taking 3 or 4 seconds in the picture, that you draw a number of parallel lines, and each time the time series crosses a parallel line, you get an event, or you call that an event. And back in the diffusion process, and therefore the XDT is given here, where when you have a bump, like the blip in the heartbeat, you get a large number of events. And when in the time interval between the two bumps or blips, you get a few time series, and it's that distribution in time that tells you the nature of the time series you're examining. So the X of t, you take these time series that have these bumps, and you integrate in time to give you this xt trajectory. And these xt trajectories can be inserted to give you an ensemble. What you want to do is you want to break up a 20-second interval and show that each of these, the black gives you the black of the split. When you do the entropy versus log of time, you get these three curves that correspond to the 20-second intervals of these time series. And you see that these very different looking time series, when processed in this way, give rise to these very closely nearly parallel lines. So the slopes are similar. And this is obtained by this going from the empirical time series and diffusion process that you integrate in time to get a trajectory x of t. Then you get an ensemble of trajectories, all of which start from a crucial event, and that gives you a histogram for the PDF, and that histogram is put in the p log p, and that gives us the slope with yielding the scaling index delta. So how can we detect the crucial events using the diffusion entropy analysis? And this is what you find, is that in these 20-second intervals that you find the time series very similar. and but they don't stay the same over time. This becomes a quasi-periodic change in the time series produced by the respiration and the time series produced by the ECG, and also in every one of the time series in the EEG. So this shows you that these three time series over a 15-minute period has this remarkable tracking ability, that they interact so strongly because they're in synchrony with one another. And it's this synchronous behavior that allows for the information change between the brain, the heart, and the lung. There's another thing that we found about this, is that this mixture of crucial events is important because there's what causes this breakup of the. Why don't they just become sinusoidal or track each other more strongly? And that's because you don't have pure crucial events. You have you generate a time series. You're looking at a time series E of t that's epsilon time is the probability of the event being measured as a crucial event. That's times the eta of with a delta less than 3 times t, plus the probability of not having not being a crucial event is 1 minus epsilon, and epsilon is with a delta greater than 3 and t, and so this is the superposition that you're tracking in the probability when you use the DEA. You're using it on this two-state process, so that the 66 curves in the figure each have a phenomenon which we call complexity synchronization, or CS. And that would be exact if you had just crucial events, but you have crucial events in that's why you have multifractal dimension for each of the time series. So the multifractal dimension indicates how information is encoded with it, an organ network time series. And the dimensional encoder that facilitates efficient communication across multiple time organ networks. Now, in addition to this communication, this assists in diagnosing when the number of non-crucial events exceeds the number of crucial events is an unhealthy situation. So the HRV time series have an inverse power loss spectrum, and cardiac pathologies can be quantified using the loss of complexity. And if we look at the autocorrelation function is the product of the two time series, the cross correlation of the two time series. When the time separation between the quantity, the two time series is unity, that should be 0. But if it's a pure crucial event time series. However, it's not. It's the square of the probability of it being well, that's pointed out here. Delta is the the scaling of the time series as a function of epsilon squared, that first order moment, that moment that's the correlation across one unit in time. And if this is a population of that was taken, in which the known data sets the population of people that have they've had heart. Well, they're pathological individuals in that their heart rate is not normal. They've had a heart attack, and the other population is healthy individuals, and you see that the delta and in the two-dimensional plot, these are the pathological individuals that have had heart problems, and these are healthy individuals. And if you look at just delta, take A, B, C, and D, the difference between what happens with a person that's considered to have congestive heart failure and those that are healthy. This is what's drawn here. These are the since these are multifractal dimensional, these time series are multifractal dimensions. You can do a time series analysis, and you find that the person that's ill, has a much narrower time series than the three individuals, the B, C, and D, that have the same delta, but the time series are much broader. And this delta can be used as the width of the multifractal spectrum as a measure of how the heart is driven by sympathetic and parasympathetic signals from the brain. And you can actually, it has this procedure has not been used so far to predict a oncoming pathology, but it can be used that way. So we have our takeaway messages now. A diffusive time series generated by an XOT is a homogeneous random fractal having a self-similar scaling index delta, giving an instantaneous measure of how organ networks complexity used in fractal dimension D is equal to 2 minus delta. The scaling index is typically time dependent and capturing the multifractality of the organ network time series. Complexity synchronization is the mechanism necessary to coordinate the time-dependent scaling behavior of the time series for synchronous organ networks, and is quasi-periodic and has been verified for EEG, ECG, and respiratory time series. Complexity synchronization is a newly identified evolutionary mechanism devised by nature to enable each organ network within a network of organ networks to continue performing its proper organ function while contributing to the proper global function of the network of organ networks. Two organ networks interacting via complex events, crucial events, result in the information transfer from an information-rich organ network to an information-poor organ network without loss of information. This occurs in, for example, in arm and arm walking. There's been multiple experiments done, and the results of that are that it's a casual observation that any two people walking along, sometimes more than two, walking along and not in contact with one another, fall into steps with one another. That's a perturbation of the time steps in the stride intervals, and this is and this has been carried out. A number of experiments by Dept in France has done experiments in which you take an elderly person with a neurodegenerative disease that affects their stride interval, their gait, and so the delta of their gait is much lower than it should be. And they put them in, they assign them a much younger person who has a normal stride interval, and that the younger person walks arm in arm with them for an hour a day for, I think it's 3 or 4 weeks. And you find that at the end of that time that the elderly person's stride delta measure of the stride interval approaches that of the healthy individual. And so the information is transferred from the healthy younger person to the information poor elderly person. And that seems to persist for a number of weeks after the experiments have been carried out, and is explained by this complexity synchronization. The multifractal dimension indicates how information is encoded within organ network series. The dimensional encoding facilitates efficient communication across multiple ONs. The transfer of information is optimal across a network of networks made up of crucial event time series. And then this is the biggie. All the physiological time series require a communication network of organ network that utilizes the fractal calculus, because all the time series received, stored, and transmitted by the network of organ network, that is, the human body, has multifractal dimensions. And it's the multifractal dimensions that come from the solution to that simplest of the fractal diffusion equations, the fractal anomalous diffusion equations, that gives rise to the scaling probability density. And to summarize these complexity synchronization properties, the complexity synchronization quantifies the most efficient transfer of information between organ networks. Complexity synchronization is a newly identified evolutionary mechanism that enables the organ network to perform its proper organ function while contributing to the proper global function of a network of organ networks. Complexity synchronization provides a totally different way to understand the dynamic response of an organ network perturbed by multifunctional dimensional scaling in health, disease, and the bidirectional transition between. Complexity synchronization can only be understood using the solution to the fractal calculus, using the fractal Fokker-Planck kinetic equation. So I end this with a hypothesis. A compromised organ network can be rehabilitated to a higher level, to a healthy level of functionality using a protocol for its being systematically driven by a second real or simulated organ network having the multifractal dimensional properties of a healthy organ network. Thank you for your attention. I hope you enjoyed the seminar. Is there time for a question or two?
Yes, we do have some time for questions. Thanks for the talk. For questions, please raise your hand. I'll call out your name as they appear on my screen. Okay, I don't see any raised hand, but if you still have a question, you can unmute your mic and go ahead.
Yeah, hi, this is Mike Schlesinger. I have a question. Bruce, do you know if there's been any studies of this on the space station where you have no gravity, how that affects multi-fractal situations?
No, not to my knowledge, but it seems that gravity would affect all of the organ systems uniformly, I would think. So I'm not sure what kind of difference you would see in the interactions among the systems when they're all being biased in the same way by the influence of gravity. But on the other hand, you're in a zero gravity environment, and the multifractals have been adapted to within the zero gravity environment, so it may have a catastrophic effect long term.
Yeah, I think that'd be a good proposal to NASA for someone to study that.
Thanks, Mike. Yeah, that would be that's interesting. Yeah, I never thought of that.
Do we have more questions or comments? You may please unmute your mic. Probably no.
Okay, then I have to ask a question as well, Mike. Mike mentioned gravity. I mentioned something even worse. I had a burst aneurysm 2 years ago, and after that, I didn't even know how to brush my teeth or walk anymore. So I had to learn all of this from scratch. Now, when you think of it as a complex system, what's the chance that it's self-organized in a way that all the critical exponents get back to the same values, meaning that I move more or less the same as I did before?
That's intriguing because remember the slide where I had everything in red, that one quotation in red, or that one statement in red. That was the identification of the fact that the multifractal dimension has to be the same because all these networks that are performing different functions and interacting differently have to communicate with each other, and they communicate with each other via the multifractal dimensionality. So the multifractal dimensionality is the same as saying that they have a common language, and that common language is the way in which the time series that gives the instruction is modulated by this delta factor.
Yes.
And so that when you have a, for example, say you have an operation on your lungs. It used to be that you would then put on a ventilator which had a periodic ventilation.
Right.
But we now know that that's not good, because your normal healthy lung has a fractal, has this multifractal dimensionality associated with it. That's what has to be captured in the rehabilitation. So this and the calculations led a colleague of mine, Alan Much, who's a physician, to do the experiments, well, to do the data processing when an individual presented himself or herself in an operation, and they found that by giving what they call the biologically variable ventilator rather than the periodic ventilator, that all the indicators for reestablishing health, like oxygenation in the blood and so on, were up some by an order of magnitude, but all were enhanced. So this the artificial nature of the variable, biologically variable ventilator proved to be really important in the person regaining their health, and that we generalized to one of the books that's up on the screen was called the Crucial Event Rehabilitation Therapy, and that is that whenever you have an illness that that's produced by an injury or a multi-variable, multi-dimensional, fractal dimensional variation that's not that's less than normal. That if you want to be healthy, you have to find a way to non-invasively introduce the perturbations or the perturbations that lead one to a healthy outcome, or lead one back to a healthy time series for the organ network that's been compromised.
Right. Thank you. That's an intriguing answer, Bruce. And I'm glad to say that I'm more or less walking the way I did before. So you seem to have a good point there. Thank you.
Oh, you're welcome.
Yeah, hi, Bruce. It's Mike again. So you're treating multifractals as an evolutionary emergent behavior, and you mentioned Darwin. So at what point in the evolution of life did we move from into multifractals? What's the first organism that would show multifractal? That could be an interesting question.
Well, and as far as the evolution is concerned, the recent developments called punctuated equilibrium, that which is the most recent version of the of Darwin's evolutionary theory, is punctuated equilibrium, where you don't have a slow. It used to be thought that you had this slow change in adaptability, and so you evolve over time. But it turns out that there's no indication of that in the fossil record. What the fossil record shows is that you had a species that behaved in a certain way for a long period of time, and then all of a sudden there was this punctuated equilibrium, which was a new adaptation all at once, and then things progressed so that the this punctuated equilibrium theory is nature's way to rehabilitate or to improve the stock of the lineage in the evolutionary chain. Did that make sense, or was I wandering?
So maybe one of those punctuated equilibria was the emergence of multifractals.
Yes, in evolutionary theory, except the fellow from I think it was Harvard. What was his name? He wrote an 1,100-page book.
The Gould.
Say again.
Was it Gould?
Yes. And in that book, he explains why that's necessarily the case for evolution of the species. But he died before fractals were commonly used. He died about the same time that Mandelbrot was introducing the notion of fractals.
I was at a conference with Mandelbrot and Gould, but Gould didn't get into fractals.
Yes, right. What year was that? You recall?
No. It was from Mandelbrot's 70th birthday. So that had to be 1994, something like that.
Yeah, 95, 96.
Something around then.
Someone, do you have a question? You can unmute your mic. Osama, are you here? Okay.
Yes.
Yeah, you can ask your question, please.
Yeah. Okay. Hello, Dr. West. Thank you so much for the nice presentation. I have a simple question. If the time series is corrupted by noise, how can this affect the detection of the crucial event?
How can what fit the Gaussian?
If the time series is corrupted by noise, how can this affect the detection of the crucial events?
I don't understand the question.
If the time series is very much noisy, so how does this will affect the crucial events detection?
Well, there are techniques if you have a signal that has, say, an inverse power law distribution, and then you impose Gaussian noise on that. There are ways of screening the one out. As a matter of fact, that's what the diffusion entropy analysis does. If you have a time series that consists of crucial events and non-crucial events, and say the non-crucial event is just Gaussian noise, then as delta becomes stronger, which means you have more crucial events than the noisy events, you'll see them. But that's the typical case, because crucial events are usually invisible because they're in a noisy environment, and so you don't see them. And so you have to use a special technique like DEA, diffusion entropy analysis, in order to separate the influence of the crucial events from the influence of the noise. That's what happens when you have a heart attack. That one figure I showed, that. Let's see, where is that? There, that all the people below the diagonal are those that have had pathological incidents in their heart rate. And so you can't judge the health of a person just by what their delta is. You have to look at what the probability, the epsilon squared is as well.
Are there any more questions? You can unmute your mic and go for it. Probably no. So I believe this is a very good point to close this talk. We thank again Professor West for this interesting talk. Thank you very much for joining us today.
Oh, my pleasure. Thank you very much.